right. Well, good morning, everybody. While you're rolling in, we'll do a soft start here. I will try to remember to make an announcement in a couple of minutes. So we are changing tack now. This is kind of a pivot point in the semester. We have been doing supervised learning. We've been living up in the supervised learning space at our taxonomy. As you know, as when we're doing supervised learning, we have examples X and we have labels. And we're going to now spend a few lectures and a few weeks talking about unsupervised learning. This is a maybe an initially less well known to some of you part of the machine learning curriculum, but it's a very important part of the curriculum. And the way to think about it is it's about trying to understand the features that go along with example. So we don't have labels anymore. Our data now is what we've been thinking about as our features. So that's our data. And you can think about the task in unsupervised learning as one of finding a summary of an example. And why might you be interested in finding a way to summarize an example? Well, you may be helping a human analyst to understand what that example is. You may be trying to identify concepts that then can feed into a supervised learning algorithm as well. Oftentimes we talk about doing semi-supervised learning, where we have a lot of unsupervised examples, and then we have a smaller number of supervised examples. And unsupervised learning, in a sense, can also be part of the pipeline towards actually building supervised learning models. So we're going to be talking about clustering today. We'll be talking about embedding in around a week from now. Here's just a cartoon of a clustering problem that's probably intuitive to you. The types of things we'll be talking about, just to give you a few examples. Here's a dendrogram. You'll know what that means in a little while. Describing the results of running a clustering algorithm on animals. So here there are 50 animals. Each animal is associated with binary features, where there are 85 binary features, like smelly, or likes water, or has a long neck. And as you kind of look at this, you can probably see that kind of hierarchically, this method has clustered together animals that are similar to each other. Down here, here's a humpback whale and a blue whale. At some point begins to be clustered with a dolphin and a seal. At some point gets clustered with a walrus and a killer whale, and so forth. Here's an example of a clustering algorithm run on gene regulation data, trying to understand the way genes are regulated. This will probably be meaningful to some of you, and probably for many of you, these words will not mean very much. I talked about this right at the start of the semester. This is Google News. This is Google this morning, clustering together different news stories to avoid information overload so that we know what it is that we want to read about just getting lots of the same stories over and over again. And the other thing that we'll think about in addition to clustering is what we'll call embedding, which is finding a lower dimensional space to represent high dimensional data. So here we've kind of asked, what is the one-dimensional line that is a good representation of this two-dimensional data? I love this example. This is embedding genetic data from across Europe using what's called PCA, principal component analysis. And what principal component analysis does is it tries to find, in this case, 2 dimensions, so try to represent as much of the variation in the data as possible. In this case, the variation that it's capturing is amongst the genetic information in the populations of different countries. And what we've done here, we have a 2-dimensional embedding of this very high dimensional data. And we've also color-coded the map of Europe. And interestingly, you can see kind of the correlation. You can see the connection between the geography of Europe and where the genetic information has been embedded in this 2-dimensional space. So this embedding here knew nothing about geography, And yet somehow you see we've got Switzerland and France kind of in the middle of the PCA embedding. We've got Portugal and Spain down here. We've got Russia up here. So it's kind of this really interesting where it's discovered in a sense the geography of Europe, obviously reflecting the way the genetic pool has evolved over time. I think I showed you this example at the start of the semester. This is taking PCA analysis, embedding style analysis to Nielsen scanner data, and trying to find a component that shows the recession of 08, 09, which we see here. Here's a cube. Remember, we've been up here doing supervised learning. So now we're doing unsupervised learning, no labels. And we'll be initially doing this in a non-probabilistic way. And we'll be thinking about our data generally in a discrete way, because we'll generally be thinking about trying to cluster the items together, which is, at least for today's class, we'll think about as a discrete problem of trying to make a hard assignment of examples into clusters. So just before we dive in, I just want you to develop a few intuitions about clustering. Here are some data points in a two-dimensional space. And it's okay, what's a reasonable clustering? Well, probably most of you would cluster the data this way. I would encourage you to think about why you think this is a good clustering of the data. And here's some more data. And I think probably most of you would think to cluster the data this way. And again, I would encourage you to think about why this might be a good clustering. And we'll be interested in fine clustering algorithms that can cope with the non-convexity of the cluster classes here in this example. So that's a little bit of warm up. Finale, I know that you do think about clustering in some of your settings.
We do, and actually this broader question of unsupervised learning in our settings comes up a lot, because one thing, actionable thing that the clinicians want to know is that, here are a bunch of kids with autism. Are there many kinds of autism? This is work that I did during my postdoc. Here are patients who all are in the ICU, or all have sepsis even in the ICU. Are there different kinds? Are there different trajectories? And this is useful because maybe something that looks like one disease, like autism or autism spectrum, is really a combination of different things, different mechanisms.
Right.
And
right.
Also there could be different, if you know that there's different trajectories, at the very least you can prepare and you can say that, okay, for this patient, this is the prognosis, this is what might happen, and this person is maybe on a different track. But the question that comes up a lot for us is really, like, does it cluster? Is it a spectrum, right? A spectrum kind of implies a sort of embedding dimensions, like the gene map that you showed. And I think these are really tough questions. Something I think is useful for the class to be thinking about is that when you get a batch of data, no one's told you that it clusters or it lies on some manifold or something like this. And so figuring out the right way to model it, there's a model selection problem here, just like there was a model selection problem in the first half of the semester.
There's a model selection problem, and there's a challenge generally with supervised learning of understanding the quality of the solution that you found. We won't get the kind of easy accuracy metrics that we've been thinking about so far in the course. Maybe the probabilistic approaches that we'll get to in a week will help with that, but generally this will be a little bit less
if you're being Bayesian, there will be only one answer and there will be one way to solve but if you're even in that setting, there's a question of like, it clusters if you believe the clusters can be stringy, but if you don't know, if you didn't think that the clusters could be stringy, then maybe it doesn't cluster anymore, right? Like this half moon example.
Right. Exactly right. Okay. So just in transitioning to talking in some more detail about this, while I think probably most of you have arrived now, just wanted to really encourage you all to attend the sections this week. We've repurposed the sections to be walkthroughs of the practice midterm questions. So encourage you to attend those and kind of benefit from being able to hang out live with other people that are thinking about the questions on the practice midterm. Hopefully you'll find that useful. All right, so I want to start introducing the formal way of thinking about clustering in a little bit more detail. As we said, we have this new task now. This new task is, you have an example and you want to generate a summary of that example. Think about it simplistically as which cluster does the example belong to? And we've talked about motivations for that. You have understanding, communication. It could be pre-training for supervised learning. Maybe you just have a lot of textual data and you don't have labels associated with it, but you want to try to cluster it in some way. You could just be trying to organizing. Try to write more clearly, organizing your data. What's our setup? So our data is just the same feature vectors we've been working with. Well, no X's, we've got no Y's. It may often be in some real space, but it doesn't have to be. It could be that it's living in some 0, 1 dimensional space or some other space. We may typically be given the number of clusters that we're looking for, but not always. You might not have anybody tell you, yeah, we think there should be 5 clusters, or we think there should be 10 clusters. And one thing that we'll think a little bit about is what is the right number of clusters, and should that be part of the input to the problem? So this may not be given. And when we're doing clustering, generally we'll think about the output as being an assignment of each example to a cluster. So the way we'll talk about this is we'll let Z n k be 0 if xn is not in cluster k, and we'll let Z n k be 1 if xn is in cluster k. So I'm using little k here to index the clusters. There are capital K clusters in total, and this Zn, which is a 1-hot encoding, is the 1-hot encoding of the cluster to which example n is assigned. And we'll think about this as the assignment. And so something to think about is, what is a good clustering? What makes a good clustering? And maybe the idea is that we want examples to be more similar to examples in the same cluster than to examples in other clusters. That's reasonable intuition for what we might be thinking about is a good clustering, that we've kind of grouped together the animals that are more similar to each other than they are to other animals. So to make that more precise, what we would need is a measure of the similarity. How do we think about the closeness between two examples? And one typical measure between two examples, x and x prime, might just be the L2 norm. So the square root of the sum of the squares of the differences between the two vectors. This is the Euclidean distance. But other things that you might think about, things like edit distances, which I'm not going to spell out how to define that in detail for strings. Probably seen some of these types of things in your algorithms classes, or things like Hamming distances, which are measuring the sum of the absolute differences in bits for bit vectors. So you can think about to define a distance metric between examples that makes sense in the domain that you're working in. But for now, we'll just be thinking mainly about using this Euclidean notion of distance, L2 norm. Any questions so far? Okay. So the first thing we'll talk about is k-means clustering. Where the idea in k-means clustering, so we'll have capital K clusters, and the clusters will be associated with a prototype, where the prototype will be the mean of the examples associated with the cluster. So what we'll do for k-means clustering is we'll define a prototype mu sub k. So this is the vector in the feature space, R to the D, corresponding to the kth cluster. So one of these per cluster, and you can be thinking, if you like, about this kind of picture where I've got some points in maybe two-dimensional space, and I'm trying to associate each of the points with a cluster, and then you can be thinking about kind of the mean of these clusters. So this might be mu1, and this might be mu2. And the goal will be to assign each of our examples. So remember, Zn is the assignment of example n, and find our prototypes, mu1 through mu capital K, such that we have a good clustering. And think about a good clustering as having each example living close to one of the prototypes. So we're trying to find a set of prototypes and a set of assignments to minimize the total distance to the assigned prototype. So I take the summation over all examples n, the summation over all clusters k. Remember, my assignment vector is one hot coded, and znk is 1, exactly for the cluster that example n is assigned to. And then I'm going to multiply that by the Euclidean distance between example n and cluster prototype k. So how to read this? This is a minimization problem, and ideally, the ideal solution to a k-means clustering problem would be to simultaneously, notice I'm minimizing both my variables here are where do I design my cluster centers, my prototypes, and to which clusters do I associate the examples in the data. And I'm trying to do that in a way to minimize the sum over all of the data of the clusters to which they're assigned. This is our objective. This is what we would like to solve if we could. This would give us a nice way to think about where the prototypes ought to live, and a nice way to think about which of the prototypes we would assign each example to. But a problem with this is that there's a non-convex optimization problem, and in fact, you can show it's an NP hard optimization problem. For those of you that have taken complexity theory classes, you know, NP hardness is a problem for scaling to large data. So we're not going to try to solve this explicitly. Raphael's asking whether ZNK is 0, 1. Yes, so ZNKs are zeros and ones. They're assignments, and they'll be one hot. ZNK will be 1 exactly for the prototype to which you assign point n. So ZNK, again, is 1 if assigned to k, and 0 otherwise. And exactly one of them is set to 1. So we cannot solve this explicitly. This is our objective. This is what we'd like to solve. But we can solve, we can describe an algorithm for k-means, which is called Lloyd's algorithm. And this is not guaranteed to solve that problem exactly, but it's a very natural algorithm and it's quite powerful in practice. So first of all, we would randomly initialize our prototypes. Just randomly position k prototype vectors somewhere in the space. And then secondly, repeat step 1, assign each example to its closest prototype. So if you want to write down for that argmin k of the distance between example k and each of the prototypes. And step 2, for each k, set the prototype to the mean of the examples that are assigned to it. So set mu sub k to the centroid, the mean, given that we're using Euclidean distance, of the assigned examples. Math for that, mu k is just 1 over nk of the sum over all n z nk xn, where n sub k is the sum over n of z nk. And we do this for each n. So let's make sure we understand this. First of all, and we keep repeating these 2 steps. So first of all, for each n, for each example, you find the prototype that it's closest to, you hard assign it to that prototype. Then as the next step, you take, for each of the prototypes, all of the examples that are assigned to it, and you find the average of the feature vector of those examples. Remember, because Z and K is either 0 or 1, when we add up this will just pick out exactly the examples that are assigned to prototype K. It'll be 1 times the examples assigned and 0 times the examples that are not assigned. And this is just the number of examples that are assigned to prototype K. And then the last thing I'll say before we look at samples is that it's typical to restart this multiple times and take the best solution, where best is according to the objective that I wrote down on the previous page. Okay. I'm going to go to show you some examples, and you can also feel free to ask me some questions at this point. Maybe you have any questions so far?
There was a very quick notation question on the PDF right before, on the notes right before you took it down.
Yep. About the summation. Yeah, that's a little n underneath the summation. That's right. I'll show you again in a second. So let's look at how this works on the old faithful Geyser eruptions. This is a big water feature in Yellowstone National Park. We have 272 examples. The features describing the examples are in one dimension, the duration of the current eruption, and in the second dimension, the duration of the next eruption. And the data has been standardized, so we've subtracted in each of the dimensions J, the mean of the feature in that dimension, and divided by the standard deviation of the feature. And so if you want to see what the data looks like, this is what the data looks like. And as you can kind of imagine, for the physical process of a erupting geyser, it will tend to be positively correlated. If the most recent eruption had a long duration, then there's a lot of pressure in the ground, and the next eruption will tend to have a long duration as well. So the data tends to be positively correlated. The way that the Lloyd's algorithm would work is you would randomly initialize the initial prototypes, say the blue cross and the red cross, and then you would, as a first step, and we'll repeat, hard assign each of the examples to its closest prototype. So these are the two, this is the initial hard assignment. And then in step 2, we take all of the blue points and we move the prototype to be the mean of the blue points. Take the red points and we move the prototype to be the mean of the red points. So we've just completed one step. Now what we do is, given the new prototypes, we do another hard assignment. So here are the new prototypes. Here's the new hard assignment where each example goes to the prototype that it's the closest to. And then once we've done that hard assignment, we again update the prototypes to be the mean of the examples to which they're assigned. Repeat again, make another hard assignment, and again, update the prototypes. Repeat again, make another hard assignment, and again, update the prototypes. And in this case, the algorithm has converged. We're also showing here the decision boundary, which is tracing the examples that are equidistant between prototype 1 and prototype 2. And you can see that the decision boundaries are linear. And Alexander is asking, so as the first step, we take one of the points randomly. You don't need to take one of the points. You can just position the prototypes anywhere in the space. It doesn't really matter. You can take one of the points if you prefer. But here we're just randomly initializing the prototypes to anywhere in the space. Okay, so it's ended up with a reasonable clustering of the examples. One thing to note about k-means is you may end up with a different clustering depending on how you initialize the algorithm, which is why we randomly restart. Here's just a picture so you can see for the Euclidean distance, so the decision boundary is linear. And you might be thinking, well, that's a problem. Maybe I want a more elaborate decision boundary. You could push your data into a high dimensional space. of course. That might be one way to make the decision boundary more flexible between the clusters. Here's another example. This is using image data from the CFAR 100 data set, where this consists of 50,000 images. Each image is a 32 by 32 by 3 representing the color RGB object. So it's 32 pixels by 32 pixels. And here we've said, please give me 16 clusters. And this is what the cluster centers look like. You can see that the prototypes are kind of averages of the images in the clusters. And here you can just kind of eyeball what examples of images in each of the clusters look like. So that's the k-means algorithm. Any questions on that before I continue? I think there was a question about notation. So this is an N. Sorry, my writing is hard to read. Any notational questions or clarification questions or conceptual questions? Okay. So I want to now just kind of help you understand what this algorithm is doing. And recall our objective, minimize over prototypes and over assignments of this quantity. What is Lloyd's algorithm doing? We can think about it as doing coordinate descent, where it's alternating between moving in two different types of directions. It's alternating between prototype and assignment updates. And so remember in our loop, so we repeat the following. Step 1, we have fixed our prototypes. Fixing the prototypes, we minimize the loss by assigning each example xn to the closest prototype. Yeah, so if I tell you that you don't get to choose both the prototypes and the assignment, I tell you these are the prototypes, and I ask you to minimize this objective, well, of course, you're going to assign each of the examples to the prototype that is closest. That's what happens in the first of our two steps. And then step 2, now we fix the assignments. So I tell you the assignments are fixed, you can't move the assignments. Now minimize loss by choosing prototypes. So what does our loss function look like as a function of the prototypes? And in particular, notice that this decouples by prototype. So once I've hard assigned examples to each of my prototypes, this minimization problem simplifies and it breaks apart by prototype 1 and prototype 2, prototype 3. In particular, you've got a bunch of examples that are hard assigned to prototype 1. How can I minimize loss? Well, I should move prototype 1 around to try to minimize loss on those examples. Its position doesn't affect the loss, the distance on any other non-assigned examples. So for prototype K, the loss, the component of the loss, is the sum over, can just write it this way, the sum over all of the examples, but it's going to exactly pick up the examples for which z and k is 1, the ones that are assigned to it. And then I'm going to take the square of the distance. Of course, I can take the square without changing the objective problem, because the square is monotonely related to the square root. So I'm allowed to take the square. So I'm now writing this as the inner product rather than the L2 norm. And now we can do things that I think we're familiar with at this point, which is we can take the derivative of this with regard to the vector, which by chain rule and remembering the rule for the derivative of the scalar product, this will be minus 2 the summation over n of z n k xn minus mu k. That's what we get when we take the derivative. And then if we want to optimize this, set that to 0. And if you push through the algebra, you exactly get that mu k is 1 over nk of the summation over n of z nk xn. So you get the expression that we were using in Lloyd's algorithm. So what is the summary of this? The summary of this is that in both steps, we're again minimizing. In both steps, fixing one part of our decisions, we minimize the other one, and then we flip-flop. We keep flipping-flop between the two. And you can think about doing gradient descents in this coordinates way. And Max is asking what would we have gotten with an L1 norm. It's an interesting exercise to work through that. You would need to think through, and you would get more of a median notion than a mean notion. And I'll get there actually in a second. So it's a nice question, Max. Any other questions about Lloyd's algorithm? I want to make just a few comments on this. So some considerations. One, how many clusters? Presentational question. This is n sub k. N sub k is the number of examples assigned to k. Any other notational questions? Okay. So how many clusters doesn't have an easy answer. On one hand, smaller, maybe better interpretation. On the other hand, larger, maybe we're doing a better job of extraction of concepts. Moreover, notice that if you think about kind of number of clusters and you think about the objective for k-means, and you think about solving that optimization problem as you increase the number of clusters from 1 to 2 to 3, etc. This is just going to keep getting better and better and better and better and better. It's just going to keep improving. So there's no point where it begins to go up again. And oftentimes what people will kind of intuitively look for is kind of what often is called a knee. This is a very informal idea. You kind of increase the number of clusters while you're still making good progress in your objective. And then that maybe is a good idea for how many clusters to use. But that's just an intuitive, informal idea. A second thing I'll say is that this is a parametric method. How many parameters are there? Well, there are d times k parameters, because you need to specify each one of the prototypes. Third thing, it's relatively inflexible. because it has a linear decision boundary. And the fourth thing is it's fast. So the computation is fast because the assignment step parallelizes by example. You just can imagine easily distributing that over a distributed computer where you can treat each of your examples separately and find which prototype is it closest to. And the prototype step parallelizes by prototype because it only works with the data that's been hard assigned to the prototype. So those are some considerations. And then just before we take a short break, I want to mention a couple of things that you can read about. One is there's an initialization approach called k-means plus plus to initialize that you'll often see if you read about the k-means algorithm. I'm not going to get into the details about what that method does. It's quite straightforward to understand. And then secondly, this was Max's question. And it goes by the interesting name k-medoids algorithm, where you can think about this as corresponding to an L1 norm, where you replace the mu k step with mu k is the example assigned to k that minimizes the total distance to the other examples in the cluster. It's maybe not exactly what you would get from L1, but if you think about median as being more in the spirit of L1 than L2, so maybe I'll just kind of write this like this. And I just show you a quick picture before we take a quick break, which is just so you can see visually the difference between the mean and the medoid algorithm. The point is that the medoid algorithm insists on restricting your choice of example. So one of the examples is actually in the cluster. So it's finding the cluster that minimizes the total distance. And that might lead to the clusters being more interpretable because you can actually now visualize the items that are representing the middle of the clusters. So I think this is a good time just to take a couple of minutes. You can feel free to ask me questions or just hang out for a couple of minutes, and then we'll talk about a new algorithm when we get started again.
There's a request if you could put up the reasons again.
Yeah, sure. Let's do that. The fourth reason is that the algorithm will parallelize. Remember, if you think about how it works, you work example by example in the first of the two steps in the round, and then you work prototype by prototype in the second of the two steps. And in both of those steps, remember the first step, you just have to compare each example to each of k types. So notice that the first step is scaling linearly in the number of examples. And in the second step, you just have to compute the average over the examples associated with a prototype, which is also linear in the number of prototypes, in the number of examples. So both of these steps in each round are also scaling linearly, number of examples. Okay. So what I want to do now is I want to talk about a alternate algorithm. Hierarchical agglomerative clustering. Agglomerative. Agglomerative. It's a hard word. So we're going to simplify and just call that HAC, HAC. Hierarchical agglomerative clustering. So our data hasn't changed. It's still the set of examples, X sub n. What we do need now, and you'll see why in a second, is we need a distance between groups of examples, G and G prime, G and G prime. So this is now a distance between groups. And basic idea of HAC is one, every example starts in its own cluster. Two, while the number of clusters is greater than one, we will merge the two closest clusters. So this is why it's called agglomerative. You start off with each example living by itself in its own cluster, and then you combine, you agglomerate, you bring things together. And you remember I showed you that kind of horizontal tree at the start of class? That's like a visualization of these merges of different clusters over time. We'll see some examples just in a second. Now, let me make a couple of notes on this. One is that it forms a hierarchy of clusters. And by the way, I put closest in scare quotes because we haven't defined closest yet. This needs to be defined. What do we mean by closest? And that's where we'll get to variations. We'll get to different forms of the HAC algorithm. So we need to, it forms a hierarchy of clusters. That's one thing that we'll see. There's no need to specify the number of clusters K. And one nice property relative to Lloyd's algorithm is it's deterministic. Lloyd's algorithm will take on random behavior based on the random initialization. And that can sometimes be a problem in practice because it means that the algorithm is not necessarily having the same behavior from run to run. And what does it need? Well, we need to know what we mean by closest. So we need two concepts. One, we will still need a distance between points. Think about L2 if you like. But now, in addition, we'll need what we'll call a linkage function to be explained in a second. And we'll typically talk about min, max, average, central. And the linkage function will let us use our distance function on examples to get a distance function on groups. So it's the linkage function that gives me my distance between groups of points. And it's that will describe which are the two closest clusters. So I'm just going to pause to make sure that those of you writing can write down what I just scribbled, and then I'm going to show you some examples of how this works. Are there any questions before we continue? Okay. So here's a first look at hack. Here's my data up here, and I'm going to build a tree down here as I merge. So initially, each of my examples, A, B, C, D, E, is in its own cluster. And then what I do is I find the two clusters that are closest, and I combine them. And let's say that C and D are the closest. As I combine clusters, I record that in my tree. So the way to read this is this tells us that we combined C with D to form clusters CD. And now I need to merge again. And let's suppose, I haven't explained the way we think about distance between groups yet, but let's suppose that A is closest to E. Of all the remaining pairs that we have, and we record that we've merged A and E into cluster AE. And now we have to decide, do we want to merge B with CD, B with AE, or AE with CD? And visually, you might think that B is the of those pairs, those three pairs, this pair, or this pair, you might think that this pair is the closest visually. So let's say that's the merge that we make, and we make a record of that in the tree. We say, okay, we've just merged CD with B to create the cluster of C, D, and B. Only one thing left to do now, which is to merge this group with this group to get all of the items. We've merged, we've built up a tree to represent what we've just done. And kind of the driving question when we think about the hack method is what is the closest, how to think about the distance between groups. So what is the closest in this example to cluster AE? Is it cluster 3? Is it cluster 2? Or is it cluster 4? And to think about this, you could imagine that one way to think about the distance between two groups is to think about the minimum distance between examples in the groups. So what is the minimum distance between this group and this group? Well, it looks like it's the distance between E and B. So in that minimum distance sense, if our linkage function was minimum, these two groups would be close to each other. Alternatively, you might say, no, it's not minimum that I think is the right way to think about the distance between two groups, it's maximum. So let me find the maximum pairwise distance between the points in this group and the points in this group, which would be, let's say, between A and H. And let me do the same thing between the points in this group and the points in this group, which would be between E and C. And then if I ask which is closest using the maximum linkage, then group 2 is closer to group 1 than group 3 is closer to group 1. And so you see that as we change the linkage rule, we change the decisions, the agglomeration decisions that the hack algorithm makes. I see Justin is asking, where do we use the L2? As a first step, you would compute the pairwise distance between all examples in your data using L2. And then so that's that little d. And then once that's the little d on x and x prime, once you've done that, you use your linkage function to build up to understand the distances between groups. So here's just a little bit of mathematics on this. Here's the minimum distance. It takes the minimum over all pairs of the L2. Here's the maximum distance, the maximum over all pairs of L2. Right, so as I said, under minimum linkage, 3 is closest to 1. Under maximum linkage, 2 is closest to 1. You can do other things. You could say, no, I don't like max, I don't like min. I care about the average distance between all of the points in this group and all of the points in this group, this expression here. Still using, let's say, L2 here, but you could substitute whatever similarity metric you like between examples. It doesn't need to be L2. You get to choose what you want to use here. Or I can say, no, I don't like average. I like the distance between the centroids. So here we're taking the mean of the examples in group 1, this point, the mean of the examples in group 2, this point, and I'm saying that that distance, that L2 distance, is what I care about. So let's go through some examples. Here's hack with min. So first of all, these two are the closest. So we merge. Then these two are the closest. So we merge. Now, is the min distance between B and CD smaller than between B and AE? Yes. So we say this is smaller than this. So we merge this one, and then we're done. And if we did it with the centroid distance, first of all, the centroid for the special case where each example is by itself, it's just the distance between the examples. So these two are closest out of all of the pairs of examples. Then we compute the centroid of that group. So here's my new centroid. And now what I want to do is say, is E closer than A, or is E closest to the centroid over here? Well, these two are closer to each other than any other thing I could do. Get the centroid of this group. And now I'm comparing these distances, B to this centroid, and B to this centroid, and this centroid to this centroid. And now this is the clustering I would form next, because this distance is smaller than this distance. So notice my tree is structured in a slightly different way. I go again, and I've completed my clustering. So just to develop some intuitions, I want you to think about this with me. Maybe you can be typing your responses into the chat. First question is, which of min and max linkages will tend to merge large clusters with each other? You say min or max, which of these two will tend to like to merge large clusters with each other? Go ahead and type what you think. That's right. So min will tend to do it because large clusters will be likely to have a pair of examples that are close to each other. And also you could say the converse, the maximum distance will tend to be large. Here's another question. Which of min and max will tend to have a chaining effect and lead to long, stringy clusters? That's not a very technical phrasing. Min or max? Yeah, look like the mins have it, because you'll tend to find other groups that are kind of nearby, and you'll be willing to kind of chain things together. One way to think about it is only one distance has to be small for you to merge. And then which of min and max tend to prefer compact clusters? That's kind of the converse, right? So if min likes things to be long and stringy, then max will tend to prefer compact things. One way to say it is that all distances have to be small for you to merge. So you're kind of looking for things that are more spherical or more compact, and you're merging them together. Average and centroid, a little bit harder to think about, but we'll just say that they tend to make compromises between allowing some elongation and preferring some compactness. So just to see the type of thing you can get, here's the pinwheel example, which would not cluster nicely with k-means because there is no linear decision boundary that separates these clusters. But if you use hack with min distance, it will be very happy to merge together the points such that 2 steps before the end, when it's nearly merged everything together, the clustering would look like this. Because it's chaining things together. It's just finding points that are close to the points that it's already brought together. Whereas the max distance would tend to end up with this kind of clustering. These are compact clusters. These are long and stringy clusters. And you can visually look at how the average and the centroid kind of compares. I guess like my read of this is that visually they look much closer to max than they do to min, but you'll see different things on different data. We're going to come back to this in a few minutes, but just to plant the seed now, one of your comprehension questions at the end of class today will be to think about this picture, and will be to think about what will min do here and what will max do here. Let me give you some examples of using hierarchical agglomerative clustering. One example is to animal clustering. This is the one I showed you at the start of class. Here are my 50 animals. Here are all my different features. This is 0, 1 example data. So each example corresponds to a 0, 1 vector. Just to zoom in on the features, a little bit hard to read. This is the bottom left of the picture. Black, white, blue, brown, gray, blah, 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 blah. Furry, hairless, tough skin, lean, flippers, etc. Those are the types of features we have. The first step is to compute pairwise distances between all of the examples. So what we've done here is we've used the Hamming distance, and we've computed the pairwise. So that's the sum of the difference between the absolute distance between the bit vectors. That's the Hamming distance. And we've just shown that in a density plot where the darker the color, the smaller the distance. You can see the pairwise comparisons between all of the animals. That would be step one. And then step two, here we've run hack with average linkage. And this is called a dendrogram. This is that tree I showed you, but I flipped it onto the side. But you can read it the same way. So the way to read this is the blue whale was merged with humpback whale. The dolphin was merged with seal. And then the group corresponding to dolphin and seal was merged with the group corresponding to whale and blue whale here. And then how to read the x distance. The x distance is the linkage cost at the value on the x-axis, say this point here, is the linkage cost when you made the merge. So as you run your algorithm, you'll be moving from left to right on this plot, because you're generally merging in a way that will lead to increases to the costs as you merge. And so you can read this as the final merge was between this group and this group, because that's the merge that happens all the way to the right. And then you can begin to read clusters off this. If you wanted 2 clusters, you would typically pull out this cluster. So all of these animals and this cluster, all of these animals here. If you wanted 3 clusters, you'd pull off this cluster, and this cluster. So you can peel back, and if you can reverse the agglomeration, wind back time, and you can pull out the clusterings that you care about. Mark says the Persian cat had his own category. Is that really true? Yeah, look at that. Persian cat lives all the way to here and then merges with Chihuahua, Siamese cat, German Shepherd, Collie, Dalmatian. Let's look at senators. These are senators from the 113th US Congress. So here are all the senators. And what is the data? It's how they voted on each of 172 bills. Did they vote yay or nay? So each row corresponds to the voting record of a senator. For example, they all voted yay, almost all of them, on this particular bill. Gray represents that they didn't vote. They were absent. So again, we can compute the pairwise distance, this case using L2 norm, and darker again corresponds to smaller distance. And we've ordered the senators by similarity here. That's where you get this block structure. And now you can do something really neat. You can run hack average on the vote on the senators as represented by feature vectors corresponding to their voting records. And this is the result. And the thing that's really neat about this is that if you color code, if you say, I just want to pull out 2 clusters. So we've just taken the final agglomeration step and we've color coded cluster 1 and cluster 2. And we cheated and we decided the top cluster was red and the bottom cluster was blue. But if you zoom in, right at the top, you've got Republican senators. Right at the bottom, you've got Democratic senators. And in the middle, you've got this transition from Republican to Democrat. And if you can see this, you've got the ones who are more kind of in the middle of the aisle, in the middle of this ordering. I've got Murkowski, I've got Collins, got Kerry, and kind of all the way at the top here, I've got the more right-wing ones. I've got Rubio up here, Rand Paul. That's probably his dad. It's probably not Rand Paul or the other Paul. At the bottom, I've got the very liberal senators, Cantwell, Gillibrand here, and Schumer. Okay, so it's kind of neat the things that you can pull out from hierarchical agglomerative clustering. Very flexible algorithm. And again, that just came from the voting records. We didn't know anything about the politics other than the kind of correlations implied through voting records. So let me just make a few comments about the hack algorithm. And then we'll move to comprehension. So one is that we can think about the average and the centroid as being compromises between min and max. Two, this is non-parametric. It's kind of instance-based. The data itself is describing the structure of the clustering. And in particular, we can have arbitrary cluster shapes. Three, this is going to scale as kind of order n squared because of the pairwise calculations. Whereas remember, k-means scales more as order n. And four, this can sometimes lead to overfitting. We'll see this in one of your concept checks, but the intuition is that it's paying attention not to averages. Kind of high-level intuition is that k-means compares examples to prototypes. Oops. Examples, xn, to prototypes, uk. And prototypes are averages. So averages are good at averaging out noise. And k-means is comparing a single example with an average, whereas hack compares pairs of examples. So there's no averaging effect. And this can lead to it being more susceptible to noise and more liable to overfit than k-means would be. So maybe Finale, you can help with setting up the rooms. We're going to move to concept check now. Let's do a concept check about clustering. Here's the form. And let me walk you through this. So again, we're going to consider this data, and you're going to be asked to think about what will hack and what will hack with min linkage do. Let me read this through with you. Will it first cluster the center, then merge the points around the outside into clusters, potentially in an unbalanced way. Then when all outside points are merged, combine with the center. Or we'll hack with min first cluster the center, then merge the points outside into some number of clusters of balanced size, then merge some of these clusters with the center, then cluster everything. Or we'll hack with min first cluster the center, then merge the points around the outside into clusters, potentially in an unbalanced way, then merge some of them with the center, then cluster all the points. And then you have the same question about max with the same answers. So I know there are lots of words, but they're the same answers. And then the second thing, this is kind of a bonus, but it gets to overfitting. I ask you to think about data considering two kinds of noisy examples. Some of the examples have all zeros in the first L dimensions, and then are random 0, 1 entries in the remaining capital D minus L dimensions. And we'll think about these as the 0 examples. And then other examples are 1s in each of the L dimensions, and then random 0, 1 entries in the remaining D minus L dimensions. We'll think about these, the X1 examples. The question is, for a large number of dimensions D and dimension L small, and with the L2 norm, and comparing distances between X0 points and X1 points. So think about a random X0 point and a random X1 point, then the distance between the 0 and the 0 will be smaller than between the 0 and the 1 with high probability. The distances between them will be smaller than the other with probability approaching a half, or the distance between the 0 and the 1 will be smaller than 0, 0 with high probability. Question 4, will hack tend to be reliable on this kind of data, yes or no? Question 5, thinking of k-means considering it's the same data, considering these two prototypes. One prototype is 0 in the first L dimensions, and then a half everywhere else. The other is 1 in the first L dimensions, then a half everywhere else. Will k-means tend to be reliable in this kind of noisy high dimensional setting? So we'll send you off. We'll bring you back in 3 minutes, and then I'll tell you the answer to the comprehension questions. All right, so really quickly here, and it seems like you all very well. I'll explain why in a second, but yes, question 1, the correct answer is the first option. Question 2, the correct answer is the second option. Question 3, the correct answer is the middle answer, because you tend to get overwhelmed by noise from the random part of the vector. And hopefully some of you were thinking about central limit theorem, where things begin to concentrate on kind of the mean of the distances across each of the dimensions. Will hack tend to be reliable in that case? No. Will k-means tend to be reliable? Yes, because the prototypes are averaging. And let me just quickly show you how to think about the hack distances. So what will min do here? Well, first of all, it's going to be merging groups with small minimum distances. So it's going to kind of pick this up because these all have small minimum distances. It's going to kind of pick this type of thing up. It's going to be willing to chain. And then it will continue merging. It kind of keeps bringing in additional clusters as long as the minimum distance between the pairs of points is small. And at some point, it will get around here where these points have the maximum distance between them across all of the points around the edge. And now the question is, does it merge? This is a crucial point. Does it merge this with this? Or does it merge one of these with the middle? Well, it cares about minimum. So it will merge around the outside, and then eventually it will merge the whole thing. That's minimum. And then now think about max. Well, hopefully you realize that max is going to get to a point where it looks like this. It's really trying to avoid bringing things together where the maximum pairwise distance is large. So it's going to get to this intermediate stage. Now what is it going to do? Well, it's going to want to merge some more of these. The max pairwise is larger than it would be with combining with the middle. So it'll do things like this. We've merged around the edges now. But now at this point, does it want to merge this with this, or does it? And notice it prefers things to be more balanced. they're not stringy anymore. Now, does it want to merge this with this or this with this? Well, it's going to want to do this with the center now, or say this with the center. And then it's going to bring additional things in with the center, and then only then will it combine everything. So it seems like most of you understood that. The 0-1 noise, maybe I'll scribble a little bit down on my iPad and I will post that to the website rather than try to walk you through it now. But it's essentially that the noise in the D minus L dimensions overwhelms the signal in the initial L dimensions and leads to these pairwise comparisons being very noisy. I'll write a little bit down on my iPad.